Kathrin Spendier is an evangelist at Quantinuum with a focus on TKET. TKET. TKET is an advanced software development kit for the creation and execution of programs for gate-based quantum computers. She received her BS in physics and applied mathematics with honors and her PhD in physics with distinction from the University of New Mexico. After a year as research associate, she joined at the University of Colorado Springs as a tenure track faculty in physics. She earned tenure at UCCS by researching biophysical phenomenon using super resolution microscopy techniques and condensed matter physics. She developed and taught over 10 different physics undergraduate and graduate courses, co-authored almost 30 scholarly journal articles, and mentored over 40 undergraduate and graduate students. After joining Quantinuum, she remains an adjunct faculty at UCCS. So please take it away.
Okay, thank you very much for the introduction. And thanks for having us and giving me the opportunity to give you a TKET workshop. So first of all, I want you to take notes so that the notebook, and do you see my mouse? Yeah, perfect. So the notebook is here at github.com/spendierk/qsite Toronto 2022. So the notebook which I'm going to go over, it's a Python, a Jupyter notebook. Take a picture, right, and then you can go download it and you can work with the code. And there should be only a few steps you need to do in order to get some accounts in order to yourself. You also can contact me. So we'll talk about TKET, so the Quantinuum's Advanced Quantum Software Development Kit for the NISQ era. And let's get started. And please do stop me. So today at the workshop, we'll talk about, give you a tutorial about TKET, about the features TKET has. And we'll talk about how to install TKET, how you get started with TKET, how you do quantum gates, how you do quantum circuits, how do you measure them, how do you move your code between different software languages, for example, like front end, and then how do you compile and run your code on back ends, and also simulators. And I will go through a lot of different examples and for you then to try out, right? Because I give a talk about this, but until you try it out yourself, you don't know how to do it, right? So that's how it works. Okay, so first of all, I want to talk about the state of quantum computers and the software development kit. So you have heard about NISQ era so far? Yes? So you know it's a noisy intermediate scale quantum. So right now, we have a low number of qubits and they're noisy. We have a lot of different noise. We not just have fidelity and readout noise, but we also have machine noise, right? We have a correlated noise and so on. So sometimes we don't even know where noise comes from. So for trapped ion computers, you have a perfect ion to start with, and then by doing all the things to it, you actually introduce noise. So, so we have this noise issue and low number of qubits, and obviously in order to do meaningful calculations, for example, if you want to crack encryption with a global search, you're going to have error correction, right? So right now we're just not there yet. So a lot of these operations are multi-qubit operations in these algorithms. So, but we can only operate between pair of qubits, right? So we're going to have to figure out how to translate our algorithm, which we come up with, actually to be run on actual machines. And then there's a lot of like software stuff and the way machines work themselves that we have to kind of decode and we have to access. So TKET so it's doing a lot of that stuff for you. And pretty much TKET is a software platform we developed for the execution of gate-based quantum computation. And it automatically handles a lot of these issues with noise, right? So you're going to have noise-aware mapping of your quantum circuit onto your hardware. So TKET is doing that for you. And it's not just the noise operations we are really good at to optimize, but we also try to be platform agnostic. So we're trying to, by knowing a lot about information about the different backends, we're trying to put that into our compiler and then put the qubits and the operations on the right qubits, right? So that you have a very optimized circuit. And I will get to this. What does it mean to have an optimized circuit for your quantum computer, for your algorithm, right? So what does it mean? So we'll go into that. So pretty much the goal of TKET is that you could, any kind of front-end language like Qiskit or Cirq, use the TKET, our quantum software development kit to make the most efficient circuit possible for your application. And then we want you to have the ability to use any kind of backend for gate-based quantum computing, right? So we want to free the user of making that decision how to talk between the different pieces so that you can actually work on your problem. So just to give a little bit of an example here, you probably have seen IBM's quantum devices. So these are superconducting quantum devices, right? And what you're seeing here is IBM Guadalupe. So for example, you have these qubits here that can talk to each other, right? So when you are routing your quantum circuit onto this back end, you have to know about which qubits talk to which, right? So how many qubits can talk to each other, and how do you have to put your circuit onto this kind of topography? That's the first step. But then you also have noise, right? So each of these qubits, because they are man-made, have error. And so, for example, you want to have a low error. These are C0 errors. So the bars are lower, the better it is. So you maybe want to work with these qubits here because they have low error, right? You maybe don't want to work with these qubits here because they have high error. So every time you do an operation, a C0 error, you are a C0 gate, like a 2-qubit gate, you're adding error. So every time you do a calculation, you add error. So maybe after 250 calculations, it's too noisy, right? And your result is just not useful anymore. And then you have coherence time. So it turns out you have learned about this, like a qubit is only alive for a certain amount of time, and then decoherence comes in, and then you lose the information, right? You lose the computation, and you don't want to run into these problems. So a very good quantum compiler takes care of this for you, and you don't have to think about it. So that's what TKET is doing. So now let's give you a little bit of an idea about what a quantum compiler is, so you can have a little bit of an idea here. So first of all, you come in with a language-dependent part, right, your circuit. Right? It could be written in OpenQuasm, it could be written in Cirq, or Qiskit, or in PyTicket, which is our Python wrapper of Ticket. Then you have an input circuit, which is in PyTicket, and then you have different phases. And these are your transpiler phases, right? So you, for example, have to first do circuit optimization, where you look for patterns in the circuit, which you try to condense, right? Then, for example, you want to do noise shaping because you want to do noise-aware mapping of your circuit. You want to convert the gates, right? So each back end has a different gate set, right? So maybe your algorithm is going to give you a Hadamard gate, but I don't know of a quantum computer right now that does Hadamard gates for gate-based quantum computing. So you actually have to rewrite your gates into the gate sets the quantum computer has, right? So that's very important. So compiler that does. And then qubit mapping is what I mentioned to you before, that certain qubits can talk to each other, but others may not, right? So you have to map your circuit onto that topography. And then once you have done all this, you have the output circuit, and then you send it to your machine, right? So what you do is you take your circuit language, right, which we can read and understand and code in Python, for example, right? We understand the language. We want to make sure that the machine can read it and implement it, right? And that's that part. It's just the analog and runtime control. And this is the part where actually TKET developers, we also help people who have hardware backends in order to apply their circuit. OK, so here I just want to do one more slide so you can see. So these are the front-end languages like PennyLane, Python, Qiskit, Quill, Quasm, right? So we can take the front-end language, convert it into the PyTicket, our Python wrapper. Then we do TKET, which is our C++ library. Then we can send it to the hardware and simulators. And here is like a slew of like a lot of different backends we have. Like we can access with PyTicket. IBM, Google, Quantinuum, which is ours, Rigetti, and so on. OK, so now let's get started in using TKET. So now you have an idea about what compiler does and why it's important to have a compiler that is doing a really good job. So you go to your Anaconda or your Jupyter Notebook or your Python layout, and you do pip install PyTicket. And then you can also do the extensions. We're called pip install PyTicket Qiskit, pip install PyTicket PennyLane. So you just take off all your packages with pip install. And here are the extensions. And I just want to show you that we have many extensions, right? So we have, these are, I couldn't fit all of them in here, but there are many extensions. We have the detailed information for all of them. One thing I want to note and want to say that, yes, you can access all these backends, but for these backends, you're going to have your API credentials, right? So you have to sign up for IBM-Q account, for example, in order to access IBM-Q, right? So by using PyTicket, you don't have automatically access to this. You still have to get the credentials. OK, so how are quantum circuits constructed? We'll talk about some basic gates, and then we'll talk about measurement. So basic gates, this is the Bell state you have maybe seen before, right? So these are entangled 2 qubits. So when you write down the Bell state, you have the wave function 1 over square root of 2 of 0, 0 state plus the 1, 1 state. And our goal is to implement that into a circuit. So you want to rewrite this in a circuit, and you may have seen that you have the bracket notation, right? And then we have gates. So we know that we have different quantum gates, and you can represent them into matrices, right? So it's a 2-qubit system. So if a 4x4 matrix, if the 2 qubits want to talk to each other, so that's the C0 gate, which you're going to see here. And that's the Hadamard gate, which you typically use in order to put qubits into superposition, right? So you can do this, and in PyTicket, you have something called the circuit class. So this is the PyTicket circuit right now, you can see. So you do the PyTicket import circuit. This is Jupyter render that gives you this nice picture here. Circ equals circuit 2. So now you make a 2-qubit circuit. And then here you apply your gates. So you're going to do the Hadamard gate on qubit 0. And then you do the C0 gate, the 2-qubit gate from 0 to 1. So you're going to have the target qubit to be 1 and the initial qubit to be 0. And here, this is the PyTicket rendering of the circuit. And it actually uses ZX calculus, which is actually something you should look into, which is a really nice, very powerful technique of optimizing circuits. But in any case, here, this is the rendering of it. And the nice thing about PyTicket is you can actually just export your circuit. You can save your picture of your circuit as a PNG and go on, which is really nice. OK, and then what I want to say here is that you are applying the circuit sequentially. OK, so that's very important. OK, so now we may want to run the circuit on the air state backend, which is a Qiskit extension. So you have to do PyTicket Qiskit installation. And then the air backend, this is your state vector generator. And then you can also ask, you get the circuit, you can run it through the air backend, and then you get the state vector out. And as you know, the state vector is this. So 1 over square root of 2 is 0.107. That's what that comes out. So you have 1, 2, 3, 4, right? So you have 4 possible qubits, 1, 0, 0, 0, 1, 1, 0, and 1, 1, right? That's what this here is. But this is the state vector, so you can calculate the state vector very easily. You also have more exotic gates, which are called parameter gates and control gates. And with this, in order to put them into your circuit, you use the op-type enum function. So here's an example of this circuit. So again, we have now circuit 3. So we have 3 qubits in this case. We import op-type, and then we have our RX gate, our CRZ gate, and we can add them together by just applying them one by one to our circuit, right, which we defined. And here again is your picture of it. And we can toggle again between ZX calculus and our PyTicket usual, like more familiar circuit rendering. But in any case, you can see here, for example, for the RX gate. Do you know what that RX gate is actually? A rotation around the x-axis at a given angle. Yes. So we rotate the 0 qubit about the x-axis at the angle of 0.5 times by angle radians, right? So you know that we actually, this is in magnitudes of pi. OK. So anyways, there are many gates. You can have device-specific gates. In this case, for example, the CC phase, this is a Quantinuum device-specific gate. Again, everything is a matrix, right? A representation. And you can implement them in your circuit, again, with the op-type function. And you are CC phase, CC max, and phased X. So these are device-specific gates, and I just wanted to show you that you can just apply them as you wish. And you can write your own gates, right? So it's very powerful. Anyways, if you want to know more about all the gates, so what you do is you go to our PyTicket manual, you get to the circuit class, and there's all the information you may need, right, for how to access the gates, how to implement them, and how you can write your own gates. And we also have symbolic circuits, so you can also have symbolic gates. Do you know what symbolic gates are good for? No? So when you are, when you do a calculation, right, and you have a function, and you plot the function x and y, and then you have x, and then you change the values, and then you plot the graph. Similar, when you have parameterized gates, you actually have to compile your circuit once, and then you change the number, and then you can figure out what your algorithm does, right? Instead of always compiling for each of the values you have in your function, which you maybe want to search over. So it's a very powerful gate, which you're probably going to use in your research. Okay, so measurement, typically, just like most of the languages we're using for a software development kit, we're measuring in a C basis, like the backends are measuring in a C basis. So we're going to have to measure in a C basis, and we can combine operations together if you want to. And here, again, have our circuit 2, we apply the Hadamard gate, CX gate, that's our Bell state. Then we call the backend, which is our air backend in this case, to get our state vector. And then we can do, we run it on our backend, which is the run function. And then this is for plotting purposes. So here you see the circuit again, and here you see the state vector output, right? So now it's a percent, like it's a 0.5, so now it's a probability, right? So we actually calculated the amplitude with this. What you can also do now is you can actually measure your circuit. And to do that, in order to actually run it on the backend, you have to measure it. To measure it, so now you have your qubits, and what you do now, when you measure them, you actually put them into a classical register. So right, so we need a classical register, because we have classical computers to get the measurement out, right? So that's what that is. So you always have to add the measure part here, and you measure it, and here we go. Now you have your measured circuit, and then what you can do is you can run it again, the air backend. That is a Qiskit backend, which is like a perfect simulator, right? So we can simulate quantum states right now, right? So we have classical simulators, and the air backend is such a simulator. So you can import the air backend, and then we run it here with the run command, right? N shots. So why do we need numbers of shots? So why don't we just run it once? Why do you have to do it 1,000 times? You know why? Yes, you need a probability distribution, right? So you need to have many, 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 many experiments in order to build up your probability distribution. That's what you see here. So in this case, we did 1,000 times. We asked the classical simulator, right, to calculate our Bell state and tell us which qubit combination we get out. And about 500 times, we get 0, 0, and about 500 times out of 1,000, we get 1, 1. So that's pretty good. So this is a very basic parts of PyTicket. So, and I want to say that you have Qiskit. Qiskit does the same thing here, right? So maybe you have seen Qiskit before. Maybe you have used Circ. Maybe you have used Q#. You maybe have used penny lane, right? So all this is good. What I'm going to tell you now is you don't have to use PyTicket if you already learned Qiskit, right? But now what I want to convince you is that you should be using Ticket in order to route and optimize your circuit, because it can make a difference. So I'm going to show you how to go between the different software packages, how to analyze the circuit and import it. OK, so again, pip install PyTicket Qiskit. So if you would like to talk with the Qiskit language, this is what it is, right? So you may have seen this from Qiskit, import quantum circuit. That's their circuit class for Qiskit. This is the way Qiskit implements our Bell state, and this is a Qiskit circuit. So you've seen that before, right? You work with Qiskit. How many of you work with Qiskit? OK, good amount, yeah. And how many of you work with something else, like penny lane or Circ or Q#? Yeah, OK. So this is what you can do, right? You can use your normal circuit, code you prefer. And then how do you go from a Qiskit to a PyTicket circuit, or Qiskit, like PyTicket, sorry, a Q-sharp to a PyTicket circuit. You do PyTicket extension Qiskit, and then Qiskit to ticket, or Qiskit, yeah, or you can also do ticket to Qiskit. You can go both ways, okay? So here you again have your circuit. So you now have your Qiskit circuit. You do Qiskit to ticket, and now you get a ticket circuit. Okay, that's it. So it's like, how many lines of code? You have to install it, 1, 2, 3 lines of code, and then you have a PyTicket circuit. So now what you want to do is you want to, you can run it in a simulator. So I just wanted to show you that you can take the ticket to Qiskit circuit and run it in a simulator with a similar code we did before. But the important part now is how do you actually compile it and route it and make it more efficient, right? So what I want to use for as an example is the chemistry-inspired quantum circuit. So how many of you have worked with chemistry? Some of you? No? 1, 2? So chemistry-inspired circuits are typically very big. So when you have like a molecule you want to do, calculate the ground state energy from, like you typically take a Jordan-Wigner mapper. And for example, you can use our software in Quanto to generate these circuits, but you can also use Qiskit's nature package to generate these circuits. And when you generate these circuits with any kind of package, you typically get a circuit, right? And you can save it as a QASM file. And then you can import this QASM file onto your, your whatever software development kit you're using. In this case, Qiskit. Sorry, Circ. No, I actually used PyTicket. Sorry. So we used here, like imported it with PyTicket QASM. And all I want to show you is that you just have a QASM file here where you have your circuit, and you import it with a circuit from QASM, and then you just render it, and I show it to you here. So here's your circuit, right? So this is a circuit for a H2 atom, which is 2 electrons, right? And this is how it looks like. And you can see it is very, 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 very long, right? So now you want to run it on the back end. So now you have to compile it and run it on the back end. You see there's a lot of Hadamard gates and so on, so you have to also put it in the right gate set. OK. Then you also can, for example, print the circuit to QASM. So here's the QASM file. I just wanted to show you that in case you're interested in how to do this. But now we actually want to do circuit analysis. So now we're going to get to the important part of what TKET can do. And I want to convince you that you should be using TKET for your research. It's a few lines of code you're going to add. It's open source, and it will help you. So let's implement our circuit. And first, let's do do analysis on it. So this is our circuit we implemented, right? So what you can do is you can actually ask, how many gates do you have? How deep is the circuit? And how many C0 gates are there, right? So how many 2-qubit gates do you have? How many total number of gates? So the total number of gates in this circuit is 150, right? And you have 56 C0 gates, okay? So again, if you see the number of gates, you should see noise. Noise should jump at you. The more number of gates you have, the more noisy is your computation at the end. So you want to reduce the number of total gates. You want to reduce the number of C0 gates. So important. So you can ask these are for analysis purposes, so you should always check your circuit, how big is it, right? OK, so now how you prepare your circuit and how you run your quantum circuit on back end. And for purposes of this illustration, I'm going to do the ideal classical simulator first, so you know what your ideal result should be. And then we're going to run it on the IBM Q emulator for Oslo, and then we're going to run it on the H1 Quantinuum H11 emulator, right? So you can see the difference about the different steps. Sorry, this is, OK. So this is the IBM Oslo. It's a 7-qubit machine, and these are the basic gate sets. CX, ID, it's an identity, RC, SX, and X gate, and that's the Quantinuum device. And here are the basic gates. So you have a U, unitary, 1Q, RC, and CC phase, right? And it's a 20-qubit machine, and this is a 7-qubit chip. And at the IBM Oslo, you have 4 qubits being connected, right? 1 talks to 0, one talks to 3, and one talks to 2. And at the Quantinuum chip, you have a fully connected chip, right? So multiple qubits. So you can talk to any qubit, more or less, depending on your gate zones. And so you want to now map that long circuit I showed you before onto these backends, okay? And you want to do it the most efficient way, because you want to reduce the error. You want to reduce the number of gates. So don't forget that. OK, I told you earlier that you have to have accounts, right, to access these backends. So you set up the IBM Q. How many of you have the IBM Q account already set up? OK, good amount. That's good. So you can use your token, your AI token. I have the information here, so in case you haven't set it up, so you can look at the notebook and do it. So here right now, you have the ByTicket extension for Qiskit, right? You're going to call an IBM Q backend. Qiskit import IBM Q. Here you have all your tokens, and you save your provider. And then you call IBM Oslo, IBM Q open. That's the open hub everyone can access when you have your IBM Q account. And then you can, for example, here you can ask the IBM backend, you can call it, and then you can print the backend info gate set. So now it tells you the gate set IBM Q works with, right? RC, I told before, use 3. It also has this CX gate and the X gate, right, for example. So now we have to take our circuit, which looked like this, and you tell me right now which is an obvious gate that's not on the IBM Q. Do you see a Hadamard gate? No, right? There's no Hadamard gate. So a Hadamard gate has to be rewritten in these basic gate sets so that the IBM machine can actually implement it. OK, so right there. And we want to implement this whole circuit onto our backend. How do we do that? You can also look at the connectivity. So here you see like the different connectivity of the qubits for this circuit, how you want to map it. So this is with get qubit graph for your backend. And now I want to talk about compilation, right? So now you want to get into compilation. So TKET has 3 different compilation levels. Qiskit has 4. So maybe you have the transpiler in Qiskit, you have 0, 1, 2, 3. TKET has 0, 1, 2. If you always call the function get compiled circuit, and then you put your input circuit here and your optimization level in TKET. You have 0, where you just map it onto the device without optimization. You have a level 1, where you do a little bit of optimization, and then you have level 2, where you do a lot of optimization. If you're interested in what the optimizations each of these levels do for different backends, we have that information on our in our manual. So just go there and look at it. So now we're going to play with level 0 and play with level 2. And I want to show you what the difference is and the result of this. So again, let's start with our compiled circuit, our circuit. And we want to compile it, right? And we want to compile it to the Oslo backend. And we're going to do 0, right? 0, which is we're just going to put it onto our backend. So remember, initially at 150 gates, right? I told you there was no H gate. There was no Hadamard gate for the IBM Q, right? So we have to rewrite the Hadamard gate. So if I now just route it onto the backend, onto the IBM Q topography, do you think the gate's going to go up or down if I don't optimize? You go up, right? And why? Right, so this should go up, right? So let's do this. Let's run it on our backend. And here, we actually go compile it, right, with level 0. We just map it. And you can now see, this is the gate set. So now we have the right gate set. And now we can ask for the numbers. So initially, we had 150, to remind you again, and 56 C0. Oopsie, sorry. It's hard to get that error. And now we have, after we compile it to the level 0, to the backend, we have 250 gates. So we actually made it worse. 114 is the depth, the layers, and 62 C0 gates. So we made it worse. So now we have more noise, right? Not good, right? So we need to fix this. So we can use our level 2. And now we use here level 2. I can't spell, I apologize. But now we use the level 2, and you see what the difference is? Now we have a total number of 84 gates, we have a layer 59, and CX gate is 25. This is significant, right? This is a factor of almost 3, right, of the 2-qubit gates. It's significant, and I want to show you the significance. You can also use the Qiskit compiler, which I did here for this circuit, and I know in Qiskit it's more like you have to do a compiler multiple times sometimes to get better results. But for the specific compiler I used here, for the Qiskit compiler, so you can again switch into the Qiskit language, right? You can then call your IBM Q credentials again, and this here is all about Qiskit compiler, right? Right here, this is the code. But if you do Qiskit compiler for this circuit, which I chose for Oslo, you actually get a total number of gates of 150-ish, I think 160 if you calculate them all up, add them all up, and you have 37 C0 gates. So I think it's easier if you show it in a table for you. So here you have the initial gate set, 150 total gates. Then we did TKET with the level 0, TKET with level 2, and here this was the Qiskit compiler. So just I want to give you attention here. So TKET had 25 C0 gates, and the Qiskit compiler used a specific one is 37. You may be getting better results. It's just a given example I'm doing right now to show it makes a difference. So my point I want to make here is this following. It's a few lines of code. TKET is open source. Use it. Use it. Check that you get a shorter, better circuit. If it works, great. If it doesn't work, OK. Sometimes people use Qiskit and TKET and other compilers together, and unison they may give you a better result. So play around. OK? Use the tools that are out there and play around. So now we want to run it on the backends. We're going to use emulators. So how many of you know what an emulator is? Right, so you try to simulate the noise, right, of your quantum computer. So because sometimes it's expensive to run on a quantum computer, so you use an emulator to give you an idea. So we do the IBM emulator, and first the noiseless one. This is our perfect simulator, right? A classical simulator. And we do our circuit, which was initially 150 gates. We run it on our backend, which is our simulator. What do you notice? We run it 100 times. So here's what I want to. Here you have the backend. You have your circuit. You run your circuit, run circuit, the compiled circuit, and you have 100 shots. And then you get the counts. And then you plot the counts, right? And you see, out of 100 shots on our perfect simulator, we got 100 times 1010, right? It's our perfect world, right? So this is what we would like to get when we run it on our backends. So now we're running on our Oslo emulator with optimization level 0. Okay? What do you guess? If you do 100 shots and you just map it, you get 250 gates. Just guess. What is the probability, or like out of 100 shots, how many times do you think you're gonna get the right answer? Just a guess. One times? Oh, luckily we're better than that. If you do it actually, you run it 100 shots. So now we again call the emulator here, right? We measure the circuit. We compile the circuit with level 0. We run the circuit, right, with 100 shots. We get the results. And now around 40 of them are, like 40-ish are in the right result, right? But you see all these, right? This is only when we run the circuit once, right, with 100 shots. So now if you think about quantum chemistry calculations, or most of the calculations, you have actually a hybrid calculation, right, where you have to do a calculation multiple times. You have to minimize something or maximize something, right? So you have to run the circuit many, many times. So your error is actually going to get worse the more often you're going to run. Make sense? So now we'll do our TKET level 2. So here's just a gate count for you, for your different. Also, it's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 states had some type of probability, right? So this is quite a lot, and this was the highest, the 1010. So now we do a level 2 optimization with TKET. And what do you get? Level 2, you again run it, and now we get almost 70-some-ish, right? Significant improvement, right? And also what I want to show you here now you have less number of states that have a little bit, right? Okay? So it is important that you have a very good compiler. It is important that you have a quantum development kit that does this for you, that you can play with this and get a really good description of your circuit for the given backend. You want to minimize the noise, minimize the number of gates. Now, for comparison here, so you see it's less number of states, got some kind of answer, right? And the 1010 state is 73. So now I want to point out that you can get access to our Quantinuum H11 device through Microsoft Azure, right? So you can actually get a free account there, and you have a given number of credits if you want to try out the H11 backend. And the nice thing, if you apply for Azure quantum credits, you get also access to IonQ. So you can also try out IonQ for your specific application. If you do the Microsoft Azure account, I did put in here the information like you would need to do in order to install that backend and talk with TKET. Okay, information is here, but I have more of it on the website, on the GitHub folder. So now we're going to run it on the H11 emulator. We're going to do optimization level 2. Here I want to point out to you, now we actually have 17 2-qubit gates. So you went from 24 to 17. So because the way our backend works, it's a little bit, the total number of gates is actually going down again. All you need to do is you have your PyTicket extension or Quantinuum, and you have to pip install PyTicket Quantinuum for this specific example. You call the backend, you compile it to the backend, and then again you get the gate information. Okay, so I gotta do like a little drum. Here we go. That's the Quantinuum backend solution. Okay, so our trapped ion quantum computer is really good. And now we have, if you do the count, we have 95 out of 100, okay, that are in the right state. But again, to give it the content, right, if you now put that in a big loop and do many, many calculations to minimize something, right, this is still, you still need to improve on that, right, and make sure that we keep going, move forward. But it's a pretty good result, and we only have 1, 2, 3, 4, 5 states. So in any case, and here's a summary. I want to tell you that if you run Oslo more often or our emulator more often, you're going to get different results, right? Sometimes you get 70, sometimes you get 80, sometimes you get 60, right? It depends. There's obviously that probabilistic effect, but it makes a difference, right? For the NISQ era, this makes a difference, and you want to make sure that you are doing it right. So workshop summary, you know how to install, hopefully, TKET, how to work with the extensions, how to work with, do quantum circuits, how to measure them. If you don't want to learn PyTicket for doing it, you can do Qiskit, then you do extension, right? You quickly change into a PyTicket, compile your circuit, run on the backends, or you can also go back to Qiskit or Circ or Penny Lane. So you can do that all. I hope I explained to you how to do this, how to run it on a backend, how to run it on simulators. If I would have more topics, if I would have more time, I would talk more about predicates and repases for quantum compilation, how to do the mapping, and then custom pass sequences. So actually, our default passes have a given passes for each backend, but we actually have many, 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 many more passes. And this is kind of like, if you don't want to have a black box, if you want to make your own passes, then you can actually do your own passes. So it could be that our default compilation passes for a backend are not the best for your application. So you should be playing with these passes and figure out what works best for you. There's a lot of useful links, okay? You can get, we have a user manual, we're in GitHub, it's open source, you can contribute, you can write extensions, you can read up on papers, and again, take your pictures. This one is the important one again. Take your pictures. If you have questions on the TKET development team, join the Slack channel, okay? And then also again, the GitHub, Spendier K, QSite Toronto 2022. That is where you have your notebook, and good luck. And if you get stuck running it, contact me, okay? Thank you.